Hi, my name is Caleb Mossy. This is my submission for the second assessment for mobile robots and manipulators. This is a module for creating a Labview simulation of a manipulator to show our understanding of designing a manipulator using Denevit-Hartenberg parameters and, of course, knowing how to use Labview. So our task has been to kind of simulate a shelf pick and place application, picking up items and then placing them on different shelves 2, 4, and 600 millimeters above the floor. In a real life scenario, this might be mounted to a turtlebot, and then the turtlebot would be moving towards the shelf, and then our manipulator would kick into action. But as it's not possible due to COVID, we've been simulating it completely in Labview, eliminating the turtlebot aspect of things. So I will flick over to the other part of my screen. This is Windows now, so we've got my Labview application here, and I've created a six joint robot manipulator arm, and if I'll run this paused for now, but you can take a look at the reach of the robot on the left here using forward kinematics. So this robot was designed specifically to complete this task, and of course just a very bare bones simulation, but you can see the mechanics here are strong, and we can see our transformation matrix here. Now if I unpause this, this is actually going to show the simulation I've created using inverse kinematics. So with forward kinematics, we're setting joint values manually and moving the robot into position. But with inverse kinematics, you can define, and often inverse kinematics is the most useful, you can define an XYZ location for your end effector and calculate the joint positions required to put the end effector at that position. Labview, the Labview robotics module, fortunately, has a plugin for this that does a lot of the thinking for us. But currently, I have it working on a custom start and end position here. So if I am to, for example, modify this start position, we can see the robot's kind of moving out a little more further to the side there, and I think I can go even further. So it's thrown an error there because this was too far for the robot to reach. I can stop, and then I can reel this back in, start it again. 0.6 was too far over there. So this is using custom set goals. So I can modify the end goal here as well. And we can see it calculates different paths depending on where it is. So that's a more effective motion, as it's not colliding with the base it's kind of set on. Now I've defined the 3 points here, so if we start with the top shelf, we can work our way down. The reason we have a start position is it's to simulate the picking motion, which I have assigned to be aside from the robot here. So let's bring that to a 0.2, a bit closer to the robot. And you can imagine it's picking up from a collection of objects here and placing it on the highest shelf there. And then if we move on to the middle shelf, a bit further down, we can see it's calculated a different motion, and doesn't look like it would be interacting or colliding with the shelving unit if we were to try and import an STL here. As you can see, this joint is maintaining quite a close radius from the base of the robot. And then the bottom shelf, just 200 millimeters off the floor. Again, I think this configuration would avoid any collisions and could be configured further with a more detailed simulation. We can modify the points in between the simulation, which of course will speed things up, but it's a less heavy simulation requirement. So if I bring this back up to 50, you can see a much smoother movement. And we can pause here. It will pause at the next end position when it reaches the goal position, and we can unpause. So I'll bring this back to about 35. And yeah, that is really completing the task that we've been assigned. So as we can see, I've also implemented sort of a visual axis to visualize the orientation of the end effector on the inverse kinematic side there. So these are my Denevitt-Hartenberg parameters. I didn't base this off of any particular robot or existing manipulator, but I would say this is quite a standard configuration. We have our joint 0 and joint 1 offset by a small amount and rotated 90 degrees to each other. I've seen this in several KUKA manipulators, but also a few other smaller companies have done a very similar thing, except this link from joint 0 to joint 1 would maybe be offset backwards. So instead of rotating like this, it would be rotating kind of like this. But I stuck with a simpler configuration here. So thank you for viewing my submission. Yeah, cheers.